Okay, so I want to talk about my favorite element, which is hydrogen. And I think you'll see why in a little bit. And it's not dense, except when we play with it, and then it gets really dense. In fact, it'll make plutonium, gold, or anything like that look like helium. They'll just float away how dense it's going to be when we get going. So I'm going to talk about harnessing fusion energy, but before I do, I want to talk about the Lawrence Livermore National Laboratory, where we have the world's biggest laser. And when you look at it, it's not normally big. It's not the kind of laser that I have here. Right here, you can see here, fits in my hand. This is a big laser. Three football fields could fit on top of the roof. So it's kind of a different kind of system than you're used to looking at. And as we go through this talk, you'll see why we built it and what we're going to do with it. So this is one of the big uses that we have for it. What is the challenge that we all face every day that you read about all the time? It's clean energy. I think everyone pretty much has come to a general feeling that is one of humankind's biggest challenges for our future, and it's for many reasons that are obvious. And right now, the world uses an incredible amount of energy, and it's going up rapidly. Right now, we use 13 terawatts of power. I don't think people know what a terawatt normally is in their lives. It's not a megawatt or a gigawatt what is a terawatt? It's equivalent to 670 billion compact laser bulbs. So if everyone on Earth put on around 100 of them, 110 of them, that's how much energy that is. Or it's equivalent to 134 billion 100-watt light bulbs or 13 billion hair dryers. Everyone on Earth had 2 hair dryers pointed at their head all the time. Their hair wouldn't last long, but that's how much energy we're using. Or 4 billion clothes dryers. Everything would be clean if that's how we did it. That's how much energy we're using right now. This is kind of an incredible thought, and it's an incredible challenge. And think about what's going on. In the next 30 years, there's going to be another 3 billion people on Earth. And if that's about 100 million a year, so every 3 years you get another United States, every 10 or so years you get another China. They're being born in places that are energy impoverished. They want their standards of living to go up. It's good for us if they do go up, but nevertheless, the amount of energy that's going to be used in the next 30 to 40 years will double to triple. Where are we getting all our energy right now? We're getting it from oil or gas. In fact, we're getting it from carbon. Fossil fuels are carbon-based. I love this picture because if you look at it carefully, at the bottom, you can see, and I don't know if you can see my little pointer, this is a 5-story high building, that shovel. And these trucks, which I have been in, been near, you could drive a normal pickup truck under the wheels, they would never touch them. So this is a seam of coal, and when this burns, of course, it goes up. A lot of that goes up in the air as CO2. When you go to smog in Beijing, or whether you go think about our climate, this is a picture that has taken on new meaning, right? This is the Katrina picture of the Gulf. What else is going on in the Gulf because of carbon right now? Sort of there's a big leak coming out of the earth where we've been drilling, and it's, that Gulf is getting polluted with carbon that we'll be living with for a long time. When we talk about how we can go forward, people talk about let's use different kinds of fuels. Could we use hydro or geothermal? These are renewables, or solar thermal, or solar photovoltaic. Are these solutions that are a part of our future? And the answer is that sometimes when you get pretty analytical about this, whether it's wind or the solar or geothermal or the kind of things that we would like, they're not so encouraging. Same with nuclear, which we'll talk about. It could be an important part of our future, but some people are a little worried about it. So what is the story of energy? This is an interesting picture. It shows the United States' use of energy over the last 150 years. And I'm going to go back all the way to 1850, where we were a wood society. And then we became a wood and coal society. And then we added a little water. You know, a few percent of our energy comes from water. Hasn't changed in the last 50 years. And then we added oil. And then we added gas. And then we added nuclear. And now this little sliver is renewables. Now, when you look at this, this is a very interesting picture to consider our future. Now, first of all, contrary to what people think, we're about a 92% carbon-based society. This is the United States, right? And what's interesting about that, 50 years ago, you know, we were a 95% carbon-based society. Not a lot has happened. This includes not only electrical fuels, but fuels for transportation and heating and the like. So we're sort of stuck in carbon land. And there's got to be a way through this. There's another story here that's really, you know, stands out. And that is in around 1975, everything started freezing up. In fact, if you look at this chart from 75 to 2010, you know, the amount of energy that we use that's carbon-based is pretty much the same as it was before. And that's because we built a lot of stuff in the 50s and 60s, and we haven't built a lot of stuff since then. You know, we've been sort of conserving our way into this environment. Is there another way for clean energy? Do we have a solution that's not carbon-based and safe? And you know, one of the things that I always think about is look up in the sky. And sometimes the answer is right in front of you. Every day, when you look up in the sky, you see the sun. That's fusion energy burning. That's hydrogen burning in the center of the sun. It's completely carbon-free, and it's available everywhere. When you look in the water that you have, which is the most common amount of material we have on Earth, there's just hydrogen everywhere. Could we get it, and could we make energy out of it? If you look up at the sky at night, it's the same story, right? Every single star you see, everything you see going on in the sky at night, except those planets, every star you see at night, the galaxies, the nebula, you know, is hydrogen burning in a thermonuclear way up there. What do we do about that? Fusion powers the sun. And Einstein taught us how that works. Einstein taught us that what's going on is that when you get things hot enough, dense enough, and high enough pressure, you can get the equation E equals mc squared to come into play. What we can do is turn mass, it's hard to believe, into energy. And when you do that, you know, a tiny amount of mass can become a very large amount of energy. The reason that is, you know, this number here, c. c is a number, it's the speed of light, and it's the speed of light times the speed of light. Speed of light is a very big number, so a small amount of mass can be a very large amount of energy. So that's what we want to do. Now, why is this so cool? Just to give you the scale of how cool this is. If you wanted to get to a 1,000 megawatt power plant, that's sort of the amount of energy that powers San Francisco, or a little bit more than San Jose or Oakland, sort of Washington or Boston, those kind of cities, 1,000 megawatts. You need 20,000 railroad cars of coal. And when you burn it, you actually get more mass out of it than you start out with, because you mix it up with oxygen, you get CO2 coming out in the air, and you get all that slag and everything else left over. What if you could produce it? What if you could do it with a million barrels of oil? Now, you have to have hundreds of super tankers. This is too expensive. Could we do it with nuclear energy? Yeah, I think that's a good idea. But the amount of energy we need in the next 30 years is equivalent to building about 1,000 nuclear reactors. That's a pretty challenging environment to take on. What if you could do it with fusion? Fusion is kind of cool because the amount of energy you would need for a year could fit in the back of a pickup truck. If you had 150 gallons of water, you know, heavy water, you could power San Francisco for a year without any carbon. In fact, the only carbon that you have in that picture would be the carbon in the gas tank that was taking it over. It was an electric car, you wouldn't need that either. Of course, you have a little carbon in those tires. So 150 gallons of water just to get that scale, that's sort of a hot tub, small hot tub of water. You could make fusion work. You would use that. No carbon, small amounts of fuel. It's non-geopolitical. Everyone has that amount of water. Trouble is, why don't we do it? Well, it happens to be that Mother Nature has made it pretty hard. You know, we don't have a sun. We wouldn't want a sun near us. We like the sun because it's far away. It's about 100 million miles away. We would have to make a very tiny sun. And when we talk about tiny, I'm talking about the scale size of a human hair. If you could make a sun the scale of the human hair, you would get enough energy out to do cities like we normally have. And what we're doing at the National Ignition Facility is exactly that. We're building the world's largest laser, believe it or not, to make fusion happen at a very small scale, but a big enough scale to change the energy equation of the world. In fact, that's a fusion target right there. That's a normal size eye, and you can get the idea of what it looks like before we crush it up, and I'll show you how we do it, into that very small burning environment. Now, I want to go back 50 years, because this is a kind of exciting time, since I'm about to talk about the world's biggest laser and how we got here. 50 years ago, actually last Sunday, right, May 16th, 1960, Ted Mayman down in Malibu, California, demonstrated the first laser. I want you to know, on May 15th, I was up at his widow's house, and I actually held the first laser in my hand. It's the most elegant device. It's about this big. And, oh yeah, there I am, right? You can see that grin. I know how I felt. So that was the first laser. And it really started a revolution that, is not just this. Almost everything we do now is based on lasers. Every time you turn on your DVDs, CDs, all manufacturing, much communications, telephones, everything you do is based on lasers. But it was pretty small. And 3 days later, at the lab, at Lawrence Livermore National Lab, which is just around 40 miles from here, you can see it, at that time, it's hard to believe it was ranch country, right? John Knuckles proposed to use lasers for fusion energy. And when he did that, he was starting a revolution that has developed equally with the laser revolution. That was get energy for the future. And we have built this SNF laser, and it's about 50 times to 100 times larger than any other laser in the amount of energy it puts out. And this is how it looks. So let me just go back. Actually, it's all done. It all works. If you can come out to see it, and we have public affairs tours all the time. So if you call up the laboratory, you can come out and see it. About 10,000 people a year get to see it. It's much better in real life than any picture, but you can see this normal Livermore person, sometimes known as a Livermoron, walking in the area. So this is pretty big. And we have these 192 beams. This is how it looks from above. And this is how it looks on the way to the target chamber where all the action is. And this is a target chamber. And you can see right here where a person normally would be if you can get the scale of it. Now remember, big laser, tiny target. This is how it works.
Count down for a shot on my mark. 3, 2, 1, mark.
This is in the control room. This is real right now. I'm going to show you a cartoon in a second.
3, 2, 1, shot.
Okay, that's the electricity that's turning it on. I'm going to lower the sound a little bit. Now we're in the master oscillator room where a very small amount of energy starts it up. Between the beginning and the end, the gain is 1,000,000 billion. Of course, this is in super slow motion. This is moving at the speed of light. Now you can see a chunk of light, and it's around 20 feet long. If you could take a movie, it would actually look like this, traveling through the laser. And when it does, every time it goes through that purple glass, it's getting more and more energy, and growing in its capability. It actually plays music as it travels. Okay, now you're looking at, talk about Lego blocks. This is the Lego block of NIF. Now, pretty soon you're going to see its cousin beams. That's 8 beams. Now you're going to see 48 beams, right? Now you're going to see another set of 48 beams, 96 beams. Same thing is going on the other side of the building. Remember, it's 10 stories tall now. Now the laser beams all have to time up. Watch this. Here they go. Now they're timed up. Now we turn them into ultraviolet colors. And now we put them into that target. Remember, that target is sort of the size of a Tylenol pill. Now we're going to watch the billionths of a second go by. Not millions, billions. Now this target is going up to millions of degrees. And when it does, it hits this hydrogen, my favorite element, and crushes it. And when it gets down to about half the diameter of your hair, you get fusion. You've built a miniature sun right on Earth. And when I talk about miniature, remember, it's real small. So some people say, is this scary or unsafe? You know, it's totally, I live in the town, right? I work there every day. It's totally safe. It's not scary. It could be our future. So let me just show you how it actually looks when it goes off.
3, 2, 1, shot.
That's it. Now we watch it a few times. Now we watch it in slow motion. This really doesn't help in any way. I just love the way it sounds. Now that's taking, spreading it out over 100 times. So what is that noise? That has nothing to do with the fusion reaction. The fusion reaction makes no noise. It's not a chemical explosion. It's a changing mass into energy. That is the flash lamps that drive the laser, like on your camera, just popping. There's a lot more energy in those than before. So how big is the target beforehand? Just to give you a scale of this is 1/16 of an inch, that big ball. And this is how it looks after when you crush it down. And you can see the width of a human hair. It's kind of amazing. And except the temperature there, which starts near absolute zero, or 425 degrees below zero, goes up to around 100 million degrees, and then almost a billion degrees in a few billionths of a second. When we do that, we unlock the power of the sun. And achieving ignition on the NIF can be a defining moment for the world's energy future. We think that if we can do this and collect that energy and turn it into electricity, you have the opportunity to make electricity and power without carbon, and it is limitless. If you look at the amount of water there is on Earth, if you just take out a few of those hydrogen atoms, it's not like the water goes away. You can run the Earth for literally billions of years. In fact, longer than there will be a sun for us to live, to be able to live on this Earth. So we're looking at how can we do this. And a facility like NIF is kind of small. So even though it's the world's biggest laser, it's smaller than a Costco. I always say if you put it in IKEA, it would be somewhere in the living room section or something like that. It's a nice small facility for making power in large amounts. And when we talk about our life engine, laser fusion energy engine, will be based on what we're doing in the National Ignition Facility over in Lawrence Livermore National Laboratory. And this is how it would go. Instead of doing one shot every a day, we would have to do shots at around 600 times a minute. So people sometimes think about, is that hard to do? Well, what does your car idle at? 600 to 800 RPM. Copy machines do this. This is the kind of thing that we think we know how to do. And what would happen is, just if you look at this, is that flash of light, would go in and hit the target. You'd make energy. It would go out to that red blanket that has literally just liquid salt in it. It'd absorb the energy. That salt would be hot. We'd run it over a heat exchanger, boil water or make hot helium, and run it past the generator, make electricity, and you're on your own. So what's really cool about it is that, and I think this is really cool, is even though it's really high tech, when you plug in your projector or your computer, it's completely transparent to the technologies that we have today, the infrastructure that we use every day for making and transmitting power. At the same time, what's also really cool, there's no pollution and there's no effect on the global climate. So over time, you could turn our carbon-based environment into a hydrogen-based environment. And the hydrogen that we would use would come from the water that's around us, small amounts of it. The state of California would need about a swimming pool of water a year. Pretty small. This is a slower motion version of it, so you can just see how it works. So you see those little targets flying in. They weigh 1 gram, which is 1/30th of an ounce, and that's how you would do it. What's cool about it? A liter of water, 1 million gallons of gasoline. It's a spectacular possibility. We have a roadmap that we would like to follow in order to do this, bring it to our society. And this is the ultimate maker project to me, anyway. This is not 1 maker or 2 makers or 3 makers or 100 makers or 1,000 makers. Literally around 10,000 makers worked on the NIF. And they're from all over the United States and actually all over the world. They did inventions from physics, inventions of engineering, inventions of technology that have changed the nature of many things that we do today. I was just listening to that little story about the plutonium pacemaker. We actually have developed capacitors that now, if you're lucky enough to need a pacemaker and have one, or self-healing capacitors to make them run for long times. Our goal is to show ignition in the next 2 years. This is not 50 years away. It's like some people think it is. It's right around the corner, and it's right in our backyard. If that works, our goal is to work with utilities and show that we can do a prototype demonstration of a power plant in the next 10 years, be commercial in the next 20 years, and be a major part of the fleet of power that exists on Earth by 2050. Some people think 2050 is a long time away. Actually, 2050 is a really important time. The world could move to 25 to 50% carbon-free by that time. The temperature of the planet would have gone up a few degrees, but we could start turning it around. This is an extremely challenging job to do. And we think that ignition using hydrogen at the NIF could be a part of that. Here's our goal. Is there fusion in our future? When I look at this picture, of a tanker coming out of the Gulf, right? What I see is something very different than what people normally see. I don't see that tanker, with fuel in it. I see that water with fuel in it. And I see the sun, which is taught us how to burn water, the hydrogen in water, to get the energy. So if that works, that's how our future will look. So that's what we're trying to do. And I think it's a great maker project. It's a different kind. It's not 1 person or 2 or 10, as I said. It's thousands of people, and I think it will affect billions of people in the future. Thank you very much.
Thank you, Ed. This is really our generation's moonshot. It gives me chills seeing your presentation. We've got time for a couple questions, and then we've got Mark Frauenfelder up.
I'd like to know your assessment of how many or what proportion of the electroweak nuclear interactions we understand, if there are any that produce fewer fast neutrons, and whether the Bourne secret doctrine has any impact on our understanding of these facts.
Yeah, I think we understand. I think we understand what's going on pretty well, and it has very little or no effect on the electroweak effect. Has no effect on this. The first order that we understand, and I think the physics of that is well known.
One more.
Your 2012 deadline, what kind of energy return are you expecting?
Oh yeah, we're trying to gain about 10 times more energy out than we put in. So that's kind of a cool idea, which I probably didn't emphasize enough. When you turn mass into energy, the goal is to get more energy out than you put in. Otherwise, it would sort of be a silly idea. And, people say, well, no scientist could ever talk about getting more out than you put in. Remember, this is turning mass into energy. The energy is there. You're just releasing it so you can use it. So a gain of around 10 to 20 is where we're heading. Be a nice number.
The 2010 prototype project, that would be hooked up to the grid?
No, that's the 2020.
2020, I'm
yeah,
sorry.
2010 scientific demonstration of what you said, gain.
And 20 is hooked up to a grid?
That would be our goal if we could get that done, yes.
Okay, great. Thank you, Ed. Really
Thank you
appreciate it.
very much.